All right, cool. So last time we made some predictions, validated some of the work, and then today we're going to look at, like, with that, solving that differential equation, what are all the other things that you can do. So last time we built our 3-story pendulum. I didn't go through and count all these stairs to figure out like how tall it was, but we ended up with 32.55 seconds, and that was a total of 5 cycles. So like 6.51 T was 6.51 seconds, the average time period that we had, or that frequency is 1 over that. 1 over 6.51, 0.153. Cycles per second, something like that. So we got two pendulums, 2 different measures of frequency. And let's just close all this stuff. We'll come up to where we are now. 2 new, so quiz 3 is up, and there's this new link to mid-semester participation. That's like your current, how you feel like current participation is going in the class. So if I open this one, kind of rough idea, like is it A, B, or C, or somewhere in between those, and then like how you feel like you are participating in the class, or if there's anything else that you wanted to say that you're connected, like especially if you're watching online, you might have a different way of maintaining your learning community. And then also like kind of thinking about how this class ties into your career story. Like, what have you been working on this semester? Is it leadership skills, teamwork? We've done like some Python and technology kind of skills. But what are things that you feel like you're doing that are helping you improve your career? And these are like specifically like 8 skills that have been identified by colleges and employers to say people that demonstrate these keep advancing. They're the ones that do well in a given field, whether it's engineering or business or marketing, any of those. Yeah, so that's our mid-semester and like late mid-semester, or like the 3/4 mark. That's all right, we'll get there. And then calendar stuff that's coming up. Let's look at our month. We're right here in the end of October. So let's go into November. The goal is that by time, when is Thanksgiving? Now I'm getting confused. What's Thanksgiving break?
23rd.
Yeah, so don't turn in the project the day after, on Black Friday, right? That doesn't make any sense. We'll change that. That was, why is it on that day? What was I doing?
Thanksgiving's weird this year. It's only 1 week after.
Yeah, once we get back, it's like we're like basically done. So maybe that was anyway. Okay, but that's we're not going to submit anything Thanksgiving week. All right. Due dates. But we're trying to get, so we'll spend like next week working on like homework 4 and then quiz 4 and project 4, and then after that week before Thanksgiving, week after Thanksgiving, I guess we're just gonna rush through because there's only 1 week left after that. We'll like build up your own projects and apply it to something. So not as much time as I had wanted, but that's all right. We'll get there. Do we have like extra time for module 4 somehow? Something happened. I swear it all worked correctly at the beginning of the semester. But we'll get there. All right, so we're looking at project number 3 today, where it's like pendulum solutions. And one of the main like equation of motion that we can derive from our free body diagram is like angular acceleration is always something times the sine of the angle. Usually we linearize it. We just say, all right, sine of theta is theta, so no need to have nonlinear stuff. But if we're going to use a computer to do it, the computer doesn't care. Whether it's linear or nonlinear, it'll give us an answer. So we'll start in this module project. We're comparing like when does that make a difference? Like what are the things that actually change when we have nonlinear answers, and when do we care? Loading. So for like here in this graph, there are 2 pendulums that one is a linear solution, so acceleration is always proportional to position. The farther it moves, the more it's going to swing back, versus that red curve is now like a nonlinear, where it's actually considering that sine of theta term, and it stretches out the time period, right? Like there's a small change in, it's still swinging between like the initial angle down to the negative of it and back up. So it's not changing like damping or anything by adding that sine theta. It's just changing what that frequency is, frequency and time period. Get into project 3. So we'll run through these. And this is for our 1 meter pendulum, but we could also compare it to our 1 Cooper long pendulum. 5.75 feet, 32.2 G. Yeah. And by changing like the length and the value of G, it doesn't really change what's happening, at least like the min and max. So the amplitude is totally independent of what the parameters, at least for the angle. If we're talking about like what the position is, then the length times that sine of the position is going to tell us like the x component. And then compare the two. It's stretched out the that time, our axis of time is have different values on it, because now we're looking at 2 periods, different oscillation, but still looks like the same answer, right? So if I want the red curve and the blue curve to be the same, what would I need to change? Because the gravity and the length didn't matter. It didn't really change what these curves look like. How would I get them to like be on top of each other? Yeah.
Can you change the start time?
The start time?
Yeah.
You want to start later in time or earlier?
I don't know.
Yeah. I don't know. So we want to change. So maybe we'll go like start at 0.5 seconds. This is going to make things weirder. All right, we'll try it. So we'll start at 0.5, go for 2 periods. And then this one is going to say we start at 0.5. And now we get, I didn't change the initial conditions though for the numerical solution. Now it's starting to offset a little bit more as I changed. Because really we changed like what our initial values were for that initial value problem. So the blue curve is still a cosine curve, but it just started being evaluated at 0.5. The red curve is a cosine, but it's offset by half a second. That was cool. Didn't quite get us there. I mean, we could try like negative term, like shifting it different directions. What else could we do? If I want blue and red curve to be like the same thing, at least like on top of each other as much as they can be. I'm going to scroll up a little bit. Well, all the way. What's the difference between equation 1 and equation 2? Yeah.
Sine theta will approach theta, and that happens for small values of theta.
Yeah, so when theta is small, then sine theta is exactly theta. Like there is no difference between sine of theta. At 0, when theta is 0, sine of theta is 0, like no error. And then when theta is like 0.001, we can check, but I'm pretty sure sine of theta is also 0.001. Yeah, pretty close, right? .01, also pretty darn close. So sine of theta is exactly theta, so that function is just returning itself. So then we need to make theta smaller, and usually the question is how small is small enough? I mean, if we just want to oscillate between 0.001 degrees and negative 0.001 degrees, then that'll work, but it's not very interesting. So what do we think? What do you think is small enough? for our initial angle. So pi over 3 is too big. What feels small? Pi over 3 is roughly like 1, right? 3.14 over 3, about 1. What feels like a small number? There's really no like lower limit to how small you think a small number is.
Pi is 180.
Pi radians is 180 degrees. But when we're evaluating like sines and cosines, it's always in radians. Otherwise, you have to like divide, like multiply by 180, multiply by pi, divide by 180, some kind of factor like that. Yeah, so pi over 3 is 60 degrees, like 1/3 of 180.
So when you say like small, we think like one angle as 1, so it's like pi over 180 or something.
180, that would be small. Yeah. So now we're going from 1 degree to -1 degrees. Our numerical solution also goes 1 to -1. And if I compare the two, I can't see the difference. So 1 degree definitely works. Like it is very small, and there's no difference whether you consider the fact that it's a pendulum swinging in a circle or it's a pendulum that's just moving in a straight line. So
if you change the first part, where's the other part that you need to change to pi over 1?
yeah, so we can walk through a little bit of what's going on. This is my main like numerical solution. So we're not digging into the details of like how do we solve a numerical differential equation, but we can tell Python like solve this initial value problem for me. And as long as this function pendulum can take these two values of theta and theta dot and return theta dot and theta double dot, then it'll give us a whole bunch of numbers that represent like what's going to happen over time. Like it keeps integrating over time and gives us the next step. So if I change the initial theta 0, then it's going to give me like the new thing there. So coming back up, if I change it from pi over 180 to pi over 18, like now it's 10 times bigger. Still pretty small though, 3 over 18. Still much less than 1. Then I get my numerical solution. And sure enough, like between 10 and 10, also basically no difference. They look like the same answers. Yeah. And we can even compare like all three values of like, here's theta, kind of going back and forth from 10 to -10. Theta dot started at 0 and then started picking up speed. And then when it got to that 0 angle, now it's moving max velocity and then it starts moving the other way. And then also like that theta double dot is going to be that G over L times our theta. or negative G over L. So it looks the same. The acceleration looks the same as position. It's just magnitude is a little different and flipped that function. Kind of cool. So we got like two different ways of solving this problem. A lot of it's kind of worked out, but there's a notebook of two different ways that you can solve the same problem. Actually, yeah, let's come down here. When you're like if you think about like swinging on a swing, what does the acceleration feel like when you're swinging on a swing? Like if you were, how would you, I mean, the angle is doing like a pendulum kind of motion. So like I go up and then I come down and then I'm up and then I go down and then I'm up. Yeah. How high on a swing have you swung? We don't have any. There was a cartoon show when I was a kid called Inside Out Boy about a kid who swang a full 360 degrees around the swing. It's a claymation, but as he went around, he turned inside out, so his whole body was like the inside was out. Yeah, it was Nickelodeon too, like Nicktoons. It was a kids show, not a like horror movie. But I'd say we could get to like 90 degrees, right? Up on a swing, close to 90 degrees off of zero. No? No. I think so. I think you can get up there. If you're really pumping, I think you can get up there. So like for a linear prediction of like what is the theta as a function of time, it's just going to say if you went up 90, you're just going to have a lot of acceleration and it's going to pull you back down really fast. But that's not really what you experience because like you almost have like a free fall for a second. Like at 90 degrees, there's not the same like linear proportion of acceleration. It's not like a spring, like you're stuck on something that's bouncing you back and forth. So numerical solution, same theta 0, I think. Yeah, same theta 0, going up to 90. There's our like theta as a function of time. Definitely, as we start getting like big angles like that, like 90 degrees, we start seeing a much bigger shift in what that time period is. So like swing sets, if you watch kids swinging on the swing set, when they're all doing small angle swings, it's all the same frequency. They're all moving at the same rate. But the kid that's swinging a lot higher has a bigger time period because now you're actually seeing that the acceleration's not G over L times theta, it's times sine theta. So then let's look at so there's our theta again, and then theta dot, kind of looks like that. And then our acceleration looks more like this, where like it hits a max value and stays there for a couple of seconds, for not a couple, like a half a second, which is kind of what you feel on a swing. Like it's not that as you're getting towards that 90 degrees, you feel like you're getting pulled back harder and harder and harder. It kind of levels out as if it's all the same and then swings you back because you're kind of maxing out that sine theta term. Anyway, so I'm just kind of playing around with this, showing you where things go, kind of an exploratory part. So this project, the questions to start with are like, what are the differences? Like, what are the things that you're seeing or measuring with your own, and you can choose your own length, your own gravity if you don't want to do it on Earth, or just if you want to change the units, make it like we just did, feet per second squared. So where are those differences and what are they? When it's asking like how do you quantify the error, this could be one example you could say is I want to know what the time period is. What is the error in the time period between linear and nonlinear? So calculate. One was 3 seconds, the other one was 3.5 seconds. In this case, where I was swinging from 90 to negative 90. This time period for the linear was like 2.7 seconds. Meanwhile, nonlinear is 3.1 seconds. So the error, the fact that I made it linear, even though it's not, is half a second, like full half second there. Or you could talk about like amplitudes as well. Like in this acceleration, we have an amplitude that's equal to some sine wave, but then the real amplitude is only going from negative 5 to 5.1 to negative 5.1. And then the last part, you can do like a little bit of Python work, like some extra stuff. Like what else do you want to compare? Some examples might be like what was the tension in the pendulum for this, or what is like the X and Y positions for this, like if you want to look at the path, or looking at like conservation of energy. So we know mgh plus 1/2 v squared should be constant since we have no friction, no drag. Yeah, so any of those are good. Yeah.
You want to code that in.
Yeah, so make like a plot of something that you can compare between the two. So like there are a bunch of plots that are made already, like T and dd theta and dd theta numerical, and oh, these are mixed up. That should be up here, right? So it matches, so the colors match. Like SOL Y1 is your theta dot, SOL dot Y0 is your theta for numerical, d theta is, yeah, your d theta dt. Yeah, so I've just been rattling on a lot. Let me check in, see where we're at, and then see if I can help with any other demos or. Yeah, kind of, but it's never going to be the same function. Right. Like if you think about the sine of t versus sine of 2t, in the very beginning they're both 0, and then immediately they become 2 different sine waves. But every second, every time the sine of 2t is done like 2 plus rotation, it comes back to be 0.
Yeah, so wouldn't that, which half of that time then go where they're the most different?
Half of the time now.
Or half of time it takes both.
Oh, where they both kind of like line up again?
Half whatever that is, or cycle here.
Yeah.
Where they would be the most different.
I don't know.
That's what I
Maybe. Yeah. As you get farther away from where.
Yeah. And then eventually there's a turnaround where they start to zero. Yeah. And I think that'd be pretty consistent, especially for the drag.
Yeah, especially for this one. This is going to keep doing the same thing forever.
Push 3. You could do like this, push 3.
Sorry.
Put it,
Oh, so we were just talking about like if you know that there's a difference in frequency, at what time are the two waves the most different from each other? So like if they're both the same value when they start oscillating, and you know one is oscillating twice, like the frequency is double the other one, then two when the one frequency of one gets back to it goes through one cycle, frequency of two has gone through two cycles. So the question was, would halfway be the max difference between them? But I think it depends on, I think halfway would actually be when they're lined up again. They're just moving in opposite directions.
oh, yeah.
Yeah. So it's almost like a quarter. And it depends on what these numbers are, though. Because, like, if this is 2.5.
So for number 1, right, we're going to write in like sentence. So the code,
For number 1,
yeah.
that one makes sense to write something. And then it always helps to have, like, a number, like something that you're trying to describe. So it's just going to show, I don't know how much you're playing around with like initial values and stuff, but if I change the initial angle to 45 degrees, it's pretty close, but it's definitely like off by a little bit. Usually my rule of thumb is 30 degrees. It just seems to work pretty well. So instead of pi over 4, pi over 6. And it's usually close enough that adding nonlinear effects are not really worth my time. So if it's less than 30 degrees, that's usually my own kind of cutoff when I'm doing dynamics, whether or not I want to consider finite rotations or just ignore them. Okay, so looking at like when the angle has the biggest difference in angle. Yeah. So part of this is just practicing like how do you describe these results? So one way of seeing it is like looking at the graph, like, hey, look, at this point in time, I was wrong by whatever, 15 degrees or something. Another way is pointing at saying, like, look, both of them look like sine waves or cosine waves, but they have different time periods. So the time period is off by 0.2 seconds for linear nonlinear. Yeah, meanwhile, if you're looking at, like, if you're thinking about amplitudes of a wave, amplitudes are exactly the same linear nonlinear. Yeah, so that's it. Okay. Yeah, there's not like a right or a wrong way, it's more just practicing and quantifying what we're talking about. This is asking for like another. So like, what else are you going to go besides just like that? Yeah. So I could show like one example. Got. So like in that last question of what else can you do? What else you got for me? One of the things that we've done is kind of look at what are constraint forces. So when we tried to figure out what are the equations of the pendulum, we ended up with two equations. One that was theta double dot is negative g over L sine theta. So that was our main like equation of motion, star. But then the second equation we got was, what was it? Negative t plus mg cosine theta equals negative mr theta dot squared. So if I know theta and theta dot, then I can calculate tension, which here I have both, right? Like I've got both the theta and theta dot because I solved that differential equation. I even plotted them. So I could write out T equals, is it negative MR theta dot? T mg. I think I'm doing this right. So they're both pointing same direction. Yeah, okay. T is mg cosine theta plus mr. Theta dot square. Minus? Am I missing? No, I'm doing things right. Today my math is not doing so well. I don't know what's going on. But I could figure out like, all right, I know tension. I can figure out what tension is. And I've got like d theta and I probably have to define like m, right? So we'll say maybe it's 0.1 kilogram, or we'll go 0.5, like 1 pound. So tension ends up looking something like this, like there's some minimum to it, and then the fast as it's swinging through that maximum value, through that, yeah, every time period ends up like going up to that maximum twice, because we have that like theta dot squared term in there. So that's my linear solution versus like, I guess I should write that out, right? It'll be the same equation, but now I'll say SOL dot Y 0 . And again, when I have like, when it's 30 degrees or less, it's probably going to look about the same, versus if I change the, I'm going to go back up here. Let's make it extreme again. Go back to 90 degrees on the swing. I'm trying to flip over. Now I start to see like much bigger differences in like the linear prediction of how much tension the cord is holding versus non-linear is much less, like only 45 newtons or something. Oh, I mixed up all the units, huh? Because I'm using feet, seconds, so this is some kind of like slug foot. Yeah, like a slug foot per radian squared or something. I don't know, some kind of weird unit. But if you stick to Newton meters, it'll be okay. So that's like one thing that you could do, or you could say, are we out of time? We're out of time. Or you could do whatever you want. Like if you want to calculate total energy, you could do it this way too. But, all right, thanks a lot.
Class next week.